Hi everyone, my name is Caitlin Fong. I am currently an NSF postdoctoral research fellow in biology. Today I'm going to talk about a project I worked on with some colleagues during my PhD, resulting in this paper, Simultaneous, Synergistic, Antagonistic, and Additive Interactions Between Multiple Local Stressors All Degrade Algal Turf Communities on Coral Reefs. All ecological communities are subjected to stressors, both at a local and global scale. These stressors typically do not occur in isolation. Rather, communities face these stressors simultaneously. This matters because stressors can interact with each other or modulate each other's effects. To clarify, I will walk you through a scenario. On the left here, we have some hypothetical response. Our first bar here is C, the control. By itself, with no manipulation, we have some response, in this case 5. We then have our stressors, A and B. Stressor A produces a response, shown in red, while the response to stressor B is shown in blue. If both stressors are applied and the response is equal to the sum of each stressor separately, then we have an additive response. This response is predictable and linear. In contrast, if the magnitude of the response is greater than a predictable linear additive response, we have a synergistic interaction. Here, the response is nonlinear and unpredictable, and it could drive an ecological surprise. If the response magnitude is less than the additive response, the interaction type is antagonistic. In this case, the response is also nonlinear and unpredictable, but produces a masking effect, where the effect of both of the stressors are dampened. The system I work in is in coral reefs. Coral reefs are among the most impacted ecosystems in the world and are threatened by multiple stressors. These stressors occur on both the local and global scale. Global stressors include things like climate change, ocean acidification, and disease outbreak. These types of stressors arise from processes that occur on a large scale and are thus quite challenging to manage. Local stressors include things like overfishing, nutrient pollution, and coastal development resulting in sedimentation. I choose to focus my research on local stressors because management is more actionable and because some research suggests that management of local stressors can help offset the impacts of climate change. So, on reefs, I choose to study these 3 stressors: overfishing, nutrient pollution, and sedimentation. Coral reefs worldwide are transitioning from coral dominance to algal dominance. This transition is mediated by turf communities. Turf algae are short, cropped algae that are a natural part of reef communities. Turf communities can be viewed as a transitional state. If turf stays short and sediment-free, these communities provide a good substrate for coral recruitment and can enhance recovery. If turf becomes long and sediment-laden, these communities are no longer good for coral recruitment and may transition to macroalgae, which is a less desirable community state than coral. So in my research, I'm interested in how multiple local stressors act and interact to affect this transitional community member on coral reefs. To do this, I conducted a field manipulation where I manipulated these 3 stressors to determine their effects. I caged half of my plots to reduce access to herbivores and to simulate overfishing. I added nutrients in the form of garden fertilizer, Osmocote slow release, to half of my cages to simulate nutrient pollution. I chose to work at a site with a lot of sediment, so to mimic the effect of a change in sedimentation rate, I brushed sediment off of half of my plots every couple of days to simulate a scenario where sedimentation had been reduced. So this was a fully crossed experiment, which means that I had all possible combinations of treatments, and we ran this experiment for a bit over 2 weeks and measured turf height at multiple time points. We found a significant statistical interaction between all pairs of stressors. What this means is that we found nonlinearities in every set of combinations. When herbivores had access, we found that the effects of nutrient addition and sediment together was additive or linear. However, when herbivores were excluded, this interaction became synergistic, or the effects of the combined stressors was greater than expected. When sediment was removed, we found the interaction between nutrient addition and herbivore removal was antagonistic. The effects of the combined stressors was less than expected. However, when sediment was allowed to accumulate, the effects of the combined stressors was synergistic, or greater than predicted. When nutrients were not added, we found the interaction between sediment accumulation and herbivore removal was antagonistic. However, when nutrients were added, the combined effect was additive. So, on the whole, all main effects resulted in an increase in turf height, degrading reefs. And we found that there was an equal frequency of all three types of interactions. So, what are the general implications of this research? First, while management of local stressors is more tractable than that of global stressors, interactions must be considered before implementation. The equal frequency of all three interaction types indicates that management of an interacting stressor has a greater chance of resulting in an unpredictable response than a predictable response, and that this unpredictable response is equally likely to improve as degrade the target communities. On a positive note, management will get more bang for the buck by managing stressors with synergistic interactions because this will have a nonlinear, greater than predicted response in the target community. Overall, we suggest that the dramatic nonlinear changes observed globally and across communities are driven by these common, strong, and nonlinear interactions. Thank you for your time.